So there, it's now started the recording. I'll try to share my screen. Then we can get started. I think that's the... Could you confirm if you can see my screen?
Yeah, we can.
Okay, that's good.
Yep, we can.
Great. So I'll just put it in slide mode, then we can get started. So once again, welcome to this training webinar for the KPEC Kenya Mathematical Olympiad. So today we shall be solving some problems. So what I can do, I will move on to the first problem that we shall be solving today. My suggestion is I can give you about a minute or so to try to put together some ideas on how this should be done. Then after that, I just got the solution. I know 1 minute is not enough to find the solutions, but just to have a go at it and see if you can come up with some ideas as well on how to go about this. If you have any immediate ideas, you can switch on your mic and share. So the question asks us to find a positive integer n such that its cube will lie between 60,000 and 180,000. And in addition, the unit digit of its cube is 3. So that is the task at hand. We have some information that the unit digit is 3. The unit digit of the cube is 3. And the cube lies between 60,000 and 180,000. So we are supposed to use that information to find the positive integer n.
Can I try?
Okay, you can share what you have.
So my thinking is, okay, does the unit digit mean the digit in the ones place value?
Yes, the ones.
So basically by trial and error, I saw that the only number which when cubed makes a 3 at the end is 7. That means this number n needs to have a 7 at the end. And then again by trial and error, I realized that 60,000 to 120,000 is from around 38 cubed to around 52 cubed roughly. So the only number ending in 7 that's in that range is 47. So I think that's my value for n.
Yeah, that's correct. So we'll now go to the solution that I have. It follows similar lines, but it's a little more formal. So I will just move on to the solution. So thank you for that solution. Now, as just following the same strategy you have, we need to find a lower bound for n and an upper bound for n. So if we check, we can see that 30 cubed is 27,000. So n must definitely be bigger than 30. And we also can see that 60 cubed is 216,000. And therefore n must also be less than 60. So that when you get the cubes across, the value of n that lie in between 30 and 60. So using the same ideas, we know that the unit digit of n cubed is 3. And this can only happen if the unit digit of n itself is 7. So if you multiply 7 by itself 3 times, 7 times 7 gives you 49. And then 7 times 9 will give you 63. So if you get the cube of a number, if the unit digit is 3, then the unit digit of the number n must be 7. So now you have only 3 possible cases to consider in the interval. You can always squeeze in this interval. This interval is a bit generous, but you can always squeeze it in so that you have fewer numbers to consider. But there are not too many to consider in there anyway. So we have 37, 47, and 57 as the only numbers that end with the digit 7. And now from this point, you can test each of them. And by inspection, you'll see that n is equal to 47 is the correct answer. Any questions? So it's exactly the same idea as used by Jeremy that we have used here. And I hope the solution is clear. If you have any questions, you can always bring us back to this problem later. For now, let's see if we can move to the second question. So the second question says that in a math contest, 50 students take part and the contest has exactly 3 problems. So there are only 3 questions in the contest. So it is known that each student solved at least 1 problem. And the total number of correct solutions is 100. So the task at hand is to prove that at most 25 students were able to solve all the 3 problems. So the largest number of students who solved all the 3 problems should be 25. So with just the given information, we need to prove this. Again, we can give a minute for anyone with ideas to see if this is solvable. So again, the task is just to prove that at most 25, the largest number of students who solved all the 3 problems is 25. It's either 25 or less, but at most 25. So any volunteers on this one with some ideas? It doesn't have to be a solution, just an idea of how to proceed.
Yeah, so what I did is that since it's known that at least each student solved at least 1 problem, then
Yes.
kind of 50 problems have been eaten up by that. So there's an extra 50 remaining since the total number of solutions is of correct ones is 100. So since the maximum that can be solved is 3, that means there's 2 extra ones. And if those 2 extra correct problems can only be split among 25.
Yes.
Yeah, so 50 divided by the extra 2 is 25. That's how I proved.
Okay. Fix something briefly, but I'm back. Now that is correct. There's we'll now look at our solution, then you can compare with yours. So what we did is the following: we set up the following system. We have three variables, A, B, and C, where A is the total number of students who solved exactly one question. B is the number of students who solved exactly two questions. And C gives the number of students who solved all the three questions. So this partitions the students into three groups. And if you add A plus B plus C, you should get 50. Because 50 was the number of students, right? So if you add up all the students, you should get 50. Now, the other thing you know is that you can add up the number of questions solved, because A student solved exactly one question. So this is the number of correct question ones. Two students, B students solved question two. Solved two questions, sorry. So, B students solved two questions. So that means the total number of questions solved here would be 2 times B, and the same for those who solved. This should be C. The last one here should be C. I think that's a typing error. So this should be 3C for those students who solved all the three questions. So each of them solved three questions. So the total number of questions solved by these students would be 3B. And the total number of correct solutions, therefore, must be 100. So now we have two equations. And if you use the two equations, you subtract 1 from 2. If you subtract equation 1 from 2, you end up with this: B plus 2C is equal to 50. So the only correction you need to do is this point here. This should be 3C and not 3B. So if you subtract this equation, if this first equation from the second one, you'll end up with B plus 2C is equal to 50. I believe you can see that. Now, that means the smallest value you can get of 2C will be 50. That is if B is 0. So 2C cannot be more than 50. And if you divide both sides by 2, you will see that C will be less than or equal to 25. So C cannot exceed 25. So the number of students who solved all the three questions will be at most 25, either 25 or less. So these are slightly different solution from what Jeremy proposed, but it still gives the same answer. So any comments or questions on this? Okay. Is there any question on this? I think we can proceed to the next question. So the next question asks, it says rather, let Y be a perfect square, which consists of 4 digits. And then we have some more information about Y. It says the ones digit and the tens digits are A and B respectively. So the ones digit is A and the tens digit is B. So suppose that the hundreds digit is A plus 1 and the thousands digit is B. The question here is, can you find the value of the square root of Y? Again, we can have a go at this. Anyone with some ideas? Any ideas, or should we proceed to the solution? This one requires a little more thought than the previous ones. That's why it's coming at number 3. As we go higher, the temperature also goes higher. Not quite in reality, but in this case, as we go to the higher numbers, the questions become a little harder. Maybe I should proceed to the answer. If there are no...
Can we have like 1 extra minute?
Okay, 1 extra minute. Fine. So you don't have to give a full solution. You can just give some pointers in what direction you're going. If you're not moving too fast, then from there we can see if you're headed in the right direction.
Can I try?
Yes. Maybe
Okay,
it's good to just identify yourself. When I'm presenting, I'm not able to see who is talking.
Oh, my name is Erica Odor.
Pardon?
My name is Erica Odor.
Erica Odor. Okay, proceed.
Yeah. Okay, so what I did was I wrote y as b, a plus 1, b, a, and then I expanded that to get 10 to the power 3 times b plus 10 to the power 2 times a plus 10 to the power 2 plus 10 b plus a. And then after that, I got 1010b plus 11a plus 100 is then sorry, is equals to y squared. And then you take 100 to the other side and you just do sum of squares. And so I got that x plus 10 is equals to 101. So that would mean that x is equals to 91. And then that means that 10b plus a is equals to 81. So then I got b is 8, a is 1. And so the answer is y is 8281. And that means that x is 91. That means that y is 91.
Okay, that was fast. We used precisely the same ideas. Let me just move on to the solution so that we can compare. So we did precisely the same thing. We expanded in terms of the thousands digits, the hundreds digit, the tens digit, and the ones or the units digit. So I think up to this point, this should be clear, because if the thousands digit is b, the hundreds digit is a plus 1, the tens digit is b, and the units digit is a. So putting the like terms together, we get this is the same as 1010b plus 101a plus 100. So we know that y is a perfect square. And again, we can find some bounds on x, right? Given the value of y, you can check that x must lie between 32 and 99, right? So this means that x squared, if you write this up here, if you bring 100 to the right hand side, you'll have y minus 100, which is the same as x squared minus 100, which is equal to 1010b plus 101a. You can split this as a difference of two square. Difference of two squares. You can factor it out like this as x minus 10, x plus 10. And also this other side, you have 101 is common. So you can factor it out and you're left with 10b plus a in the brackets. So what this means is the following. Since we know that 101 is a prime number, it must divide one of these numbers. There's a theorem from number theory which says if a prime number divides a product of two numbers, then it must divide one of the numbers. So in this case, the prime number definitely must divide. 101 is a prime number, and therefore it must divide. It's a factor of this whole number, and this whole number is a product of this x minus 10 and x plus 10. That means 101 must divide one of them. We need to figure out which one is divisible by 101. So is it x minus 10 or x plus 10? Now to do that, we go back to this inequality. If we subtract 10 throughout, right, we have 22 is less than x minus 10, which is less than or equal to 89. Okay. If we add 10 throughout, then we end up with this inequality. So this makes more sense. If x minus 10 is less than 89, then it cannot be divisible by 101. So we are left with only one option, that x plus 10 is the one that lies in a range in which it can be divisible by 101. Now, the largest value x plus 10 can take is 109. So the only option x plus 10 can be is 101. It's the only number in this range which is divisible by 101. So x plus 10 must be 101. And you can make x the subject here, and you will obtain 91. So x is 91, and x is the square root of y. So that means square root of y is what we're looking for. It's 91. You can confirm that it works by just squaring 91. And when you square 91, you get 8281. So we remember the thousands digits and the tens digits were the same. They were both b. So in this case, b is 8. So the units digits, if the units digit was a, the hundreds digit was the units digit plus 1. So again, it works here. The units digit is 1. The hundreds digit is 1 plus 1. So a is 1 and b is 8. So this fits the description in the question, and therefore our answer is 91. And we have confirmed that there's no other answer. This is the only answer in the given intervals that we were able to obtain. So any questions on this one? No questions on that. So we can move on to the last question. So now this is the final one. It says if n, let n be greater than or equal to 3, be an integer. So, and 3n plus 1 is a perfect square. So the task is to prove that it's possible to find three integers, positive integers, a, b, and c, such that 1 plus this thing here, 1 plus 3n plus 3 over a squared plus b squared plus c squared is also an integer. So we need to show that it's possible to find three such integers, positive integers, such that a squared, b squared, and c squared will give us this expression to be an integer. So 1 minute again or 2 minutes to get some ideas. Any ideas? This one looks to be a bit tougher.
Okay, so since n is greater than or equal to 3, then 3n plus
Could you
1.
speak a little louder? For some reason,
So since n is greater than or equal to 3, then 3n plus 3 will be greater than or equal to 10. So when you find x, it will
can
be...
you? I think I missed the beginning of your Jeremy.
Yeah.
I think I missed the beginning of your solution. So maybe if you don't mind, you can start again.
Okay. So I was saying, since we're told that n is greater than or equal to 3, then 3n plus 1 will be greater than or equal to 10. And then that 3n plus 3 that's inside the square root, that will be greater than or equal to 12. So to prove that x can be an integer, then that value in brackets, okay, that fraction, 3n plus 3 divided by a squared plus b squared plus c squared has to be greater than or equal to 0. So since we found that the numerator, which is 3n plus 3, is greater than or equal to 12, then we just need to prove that the denominator can be less than or equal to 12, that you can find three integers a, b, and c, which when squared add up to less than 12. And there are such integers such as 1, 1, and 1, or 1, 2, and 1. So that's how I went about it, but I'm not so sure.
Okay, let's, the general idea is good, but you need to find a much more general solution. So we will go to the solution that we have. So any integer, first of all, we'll go through some ideas that we can help us solve this. So the first idea we shall go through is this one, that any integer you're given can be written in this one of these three forms. Either it's a multiple of 3, or leaves remainder 1 when divided by 3, or leaves remainder 2 when divided by 3. So that means you can write them as 3k plus 1, or 3k plus 2. So any integer you pick will fall into one of these 3 categories. So if you consider these 3 categories, you will have considered all possible integers. So if m is a multiple of 3, if you square it, you will also get a multiple of 3, right? Now the next thing we'll look at is if m leaves remainder 1 when divided by 3, if you square m, you still get whatever you get will still give you remainder 1 when divided by 3. If you square this, you will see that. If you square this, you will have a multiple of 3 plus 1 at the end of it all. So the next thing we consider, if an integer falls in this category, if you square it, anytime you square it, you will also get a remainder 1 when divided by 3. So this squared still gives you a remainder 1 when divided by 3. So this tells us something about perfect squares. Any perfect square you have will either be a multiple of 3. If it is not a multiple of 3, the other option for it is it will leave remainder 1 when divided by 3. So a perfect square does not leave remainder 2 when divided by 3. It either has remainder 0 or 1. It's either a multiple of 3 or leaves remainder 1 when divided by 3. So we shall use this information. I hope this makes sense.
Yeah.
So that's the claim we have proved. So any perfect square can either be written as a multiple of 3 or a multiple of 3 plus 1. So we shall use this claim as we go. So, so y has 2 options. If y is equal to 3x plus 1, then y is the square of a number that is not divisible by 3, right? So if you pick y to be 3p, so it means y is the square of a number which is not divisible by 3. And that means you can write it as 3p plus 1, right? Should be a number that's not divisible by 3, either 3p plus 1 or 3p plus 2. So we first consider the case where it is a square of 3p plus a number of the form 3p plus 1, right? So then we know y is I think we can go back to the question so that I need to refer to this. Is there something I've left out? There's something I'm not seeing. Just hold on. Where am I getting y? So we'll just proceed. I think it will become, for some reason, I can't see why I'm using this. That's fine. So if y is in this form, then it means y must be a square of a number that is not divisible by 3. So if y is equal to 3p plus 1 squared, then we have 3n plus 3 will be equal to y plus 2, right? So that means if you take y to be 3n, I think I meant to use n here. That's why That's why the confusion is coming in. So I should have been consistent, either start with x or start with n. So 3n plus 3 is the same as y plus 2. You just add 2 to this. And y plus 2 is this whole quantity here, plus 2. If you square this, you will have this 9p squared plus 6p plus 1 plus 2. And this eventually simplifies to 3p squared plus p squared plus p plus 1 squared. So with this arrangement, I hope this is clear. You can see how this comes about. You can split this 3p squared can be split into 3p squared 3 times. So that you have p squared plus p squared to take the first two. And then the third p squared will be added to 2p plus 1 to give you this perfect square, p plus 1 squared. So now if you take, in this, once you set this up, you can take a and b to be equal to p, and you take c to be equal to p plus 1, right? So if you plug this back into the original equation, you should see that x will be equal to 2. So here the only thing is to be consistent with n and n plus n and x. So the second case to consider is if y is there are two cases. The first case is that y is a square of a number which is not divisible by 3. So we consider a number which leaves remainder 1 when divided by 3. Now we consider it as a square of a number which leaves remainder 2 when divided by 3. And 3n plus 3 will again be the same as y plus 2. And now you can replace y with this quantity here. And then it simplifies again to this. If you spread this out, you'll be able to split it into 3 positive numbers, p squared, p plus 1 squared, and p plus 1 squared. So if you pick a to be p, b to be b, and c to be equal to p plus 1, then again you have integers which work. They will divide 3n plus 1, or rather they'll divide 3n plus 3. And when you plug them back into the equation, you will get x is equal to 2. So we have shown it's always possible to find these 3 integers, and we have considered all possible cases. And in both cases, the integer x will be equal to 2. So we have shown the possibility and found the actual integer x. There doesn't seem to be any other possible integer value that x can take other than 2. So this gives a wide range of solutions. I hope that is clear. So that brings us to the end of the presentation. If you have any questions, you can ask. Any comments? Okay, so looks like there are no more questions, and we are done with the presentation. So thank you very much for joining us for this talk. and we'll be back again in 2 weeks' time. So hopefully in the next time we are back, we will be able to go through some geometry topic. We want to cover some more advanced concepts in geometry. So I think that's what we'll do next time. It may be more interesting to see the topics covered sometimes more than the problems being solved. So, and it would be good to change the environment and see what happens when we change, when we are solving problems or when we are covering a topic. So are there any comments? Or we can close.
I want to say the questions were very interesting. I don't know if you can hear me.
Yes, I can hear you.
Yeah, so the questions are very interesting. I still want to think through this, the final question. Is that the only way to approach it?
There are usually more than one way to approach the problem. I have not tried a different way. But
okay, I will.
Time, usually there's, in fact, most of the questions, in fact, maybe even all of them, if you sit down, you might find an alternative solution.
Okay, I will try, and hopefully I'll have something to show the next time we meet.
Yes, yes. That is fine. So even if you have it before we meet, you can share.
All right.
Okay, asante sana. So I think I will call it an evening and close the meeting for now. So have a great evening and thank you for showing up. There's someone in the chat with a comment, I think, or Felix Sandy. So, and thanks a lot to Erica and Jeremy for your contributions as well to the solutions. Jeremy has left, I think. I don't see him anymore. Okay, have a good evening. We'll meet again in 2 weeks' time.
Bye.